Hello guys, this video is about work, energy and power in rigid body mechanics. I start from the scratch. In the work energy chapter, we learned that if a horizontal force like F is acting on an object like M and it's displacing that for a distance d, the work done is supposed to be the force times displacement. And the unit of work in SI is joules. How to find the work in rotational motion? Let's say a tangential force like F is acting on this disk, and the radius of this disk is r. So this force may make a torque and rotate the object for an angle of theta. Theta is the angular displacement. Look at this. The force, as it's a tangential force, has a distance traveled on the circumference of the circle like s. Okay? And we know that S divided by r is definition of theta in radian. So S is supposed to be r theta. So to find the work done by the force, I can write F times S, force times the distance traveled by that force on the circumference of the circle. And S could be rewritten as r times theta. R, radius, theta is the angular displacement. You remember force times radius was the torque. So it's the torque times angular displacement, tau times theta. This is the work done in rotational motion. Unit in SI, same, is joule. What about the power? You remember the power was work done divided by time, the rate of the work done in every second. So let's again change the equation. I replace the work with tau times theta as we found it in the previous slide. So it's tau times theta. Tau is the net torque acting on the object and theta is the angular displacement. Theta over t, is omega, angular velocity. So it's tau times omega. Very good. It's another appearance of the power. In SI, same unit, watts. Okay? The other is kinetic energy. How to find kinetic energy in rotational motion? Suppose that I have an object of mass m moving on a circle, and this circular path has a radius of r. The speed of the object could be something like v. So kinetic energy is supposed to be a half of mv squared. The v is related to angular velocity like r omega. So let's replace it. Now I can rearrange the equation. It's actually a half of m r squared omega squared. Okay, so let's write it like that. A half of m r squared for a point mass is supposed to be moment of inertia. So it's supposed to be a half of moment of inertia times omega squared. Not for a point mass, for every object. I is general, but the approach was very simple based on a point mass moving on a circular path. So let's summarize it in a table. Quantity, work, power, kinetic energy in linear motion and in rotational motion. In linear, we had force times distance. Here, rotational is tau times theta, angular distance. Power is force times velocity, force times speed. And here, the power is torque, the brother of force, times angular speed. Kinetic energy, a half of mv squared. Mass has a broader moment of inertia, and v has a broader omega, so it's a half of I omega squared. We still are working on brotherhood. What about the work kinetic energy theorem? In the work kinetic energy chapter, I told you we have an object like m acted by a net force of F, starting with an initial velocity of vi, accelerates or decelerates due to that net force, and goes to a final velocity of vf. Still, the net force is acting on that. Change in kinetic energy of the object, change in EK, is supposed to be work done by the net force. This is the work kinetic energy in general. Do we have the same theorem in rotational motion? Of course we do. It's the same thing. I have a wheel. Let's say this is the moment of inertia I, and it starts from initial omega of omega 1, initial angular speed, and then due to the net torque acting on that, it goes to a final omega 2. Not necessarily accelerating, it could be even a decelerating motion. Not important. Change in kinetic energy, again, is supposed to be the work done by the net torque. Okay, but you know the kinetic energy is a half of I omega square. So I can write it as a half of I omega 2 square minus a half of I omega 1 square. Final kinetic energy minus initial kinetic energy. And then write it like that. Look at this question. A uniform disk of mass 0.25 kilogram and radius 0.15 meter rotates about the central axis with an initial angular velocity of 8. Calculate part A, the initial rotational kinetic energy of the disk. Okay, kinetic energy is supposed to be half of I omega squared. But first we should find the I. About the disk, we learned if it has a mass of m and radius r, I is supposed to be a half of mr squared. This just for a disk. For a sphere, it has a different formula, you know. So let's find the r first. I plug in the values, 0.25 kilogram for the mass and 0.15 for the radius. I in SI is supposed to be 2.8, 10 to negative 3. Then I plug in the I in this formula, and omega also given, initial omega 8. And the answer is supposed to be 0.09 joules. This is the kinetic energy, initial kinetic energy of the object. Part B, the work done in increasing the angular velocity of the disk from 8 to 16. Work done is the work done by the net torque. Okay, work done by the net torque is supposed to be changing kinetic energy. Okay, this is something we know. So let's do it like that. Kinetic energy final minus kinetic energy initial. And so it's a half of I omega final square minus omega initial square, as I mentioned. Then let's plug in the values. This is the I, we found it already. And this is the final omega 16, this is the initial omega 8. And the answer is 0.27 joules. This is the work done by the net torque acting on the disk. Another question. A stationary bicycle trainer has a flywheel with electrically controlled resistance to simulate different cycling conditions. When the cyclist stops pedaling, the flywheel comes to rest from an initial angular velocity of 180 in a time of 9 seconds. Okay, means that initial omega is 180, it comes to rest, so final omega is 0, and the time interval is given to be 9 seconds, okay? The moment of inertia also given, so I is 0.07 in SI. Calculate the resistive torque acting on the flywheel, assuming that it is constant. Okay, torque is easily I alpha. You know, I is the moment of inertia and alpha is the angular acceleration. Angular acceleration is delta omega over delta t. Final omega minus initial omega divided by time. Okay, so let's do it. Final omega is 0, it comes to rest. Initial omega 180, this is I, and this is delta t. So we are done. Negative 1.4 Newton meter. The reason that the torque is negative because it's a resistive torque. Part B. The work done by the resistive torque in stopping the flywheel. Okay. The work done by the resistive torque, as the resistive torque is the only torque acting on the wheel for the time being, it is the net torque. Work done by the net torque acting on the system is supposed to be change in kinetic energy. So let's write it like that. EK2 minus EK1. EK2 is a half of I omega 2 square. EK1 is a half of I omega 1 square. So let's write it like that and then plug in the values. I was given in the question, final omega, initial omega, and the answer negative 1.1 kilojoule. I have saved a 10 to 3 here for kilo. Why this is negative? Because this is resistive torque. And systematically, the wheel decelerates. So it's going to stop. So resistive torque must have a reduction in kinetic energy. So final kinetic energy must be less than the initial. So it must be negative. Part C. The power that the cyclist needs to transfer to the flywheel to maintain the constant angular velocity of 180. Here, the cyclist comes to play. It's acted by a resistive torque, okay? And also you are, as a cyclist, you are acting by a torque, like the forward torque, to compensate that dissipation of energy. Actually, your power and the resistive power must be equal. Otherwise, it comes to rest again. So the power you need to provide for this bicycle, for this cycle, is actually the same as the power it's dissipating energy with. Okay, so let's do it like that. The power is tau times omega. It's exactly like force times speed. Okay, and then tau is supposed to be 1.4. Same torque I use for the resistive torque acting on that, because my torque must be exactly the same as that. And 180 is the omega. Okay, because it should remain at the initial omega to the end, okay? Constant angular velocity. So you should keep 180 to the end. So it's 250 watts. This is the power you should provide to maintain the constant angular velocity of 180. Another question. A meter stick of mass 0.15 kilogram is suspended at one end here and can rotate freely about the point of suspension. Freely means there is no actually friction. The meter stick is set in motion so that it passes through the vertical position with an angular velocity of 3.4. Okay, when it's passing through the vertical position, it has maximum omega, okay? Because when it goes to the right and then deviates more, it's losing its kinetic energy and gaining potential energy. Here, we may think it stops, okay? Part A, calculate the rotational kinetic energy of the meter stick in the vertical position. Okay, this is exactly the maximum kinetic energy it has. So let's use the general formula, a half of I omega squared. But what was the I? About a rod, I told you if it is rotating around its center, the I, the moment of inertia, is 1/12 of mass times L squared. L is the length, okay? But when it's rotating around its end, one end, I is supposed to be 1/3 of mL squared. It's a different thing, okay? So we use this formula. Depending on the point of rotation, it differs. So let's plug in the values. Mass of the meter stick is given to be 0.15 kilogram and the length is 1. So I in SI is supposed to be 0.05 kilogram meter square. Then let's plug in the values. And this is the omega given here. Kinetic energy is supposed to be 0.29 joule. Part B, explain why the torque acting on the meter stick increases with the angular displacement from the vertical position. State the direction of the torque. When the stick is vertical, okay, there are two forces acting on that. One of them is the force due to the suspension point and holding the rod, and the other is the downward force of W. Okay, this force cannot create any torque because the center of rotation is here. A force passing through that point cannot create any torque. W also, in vertical position, it has no effect. But here, the W can create a torque. This force still is neutral because it's passing through the center of rotation. So the only force that is effective in creating a kind of resistive torque against the deviation is W. The distance for finding the torque, because torque is force times distance, the distance is supposed to be this. You should extend the force and find the line of action, and this is the distance to the center of rotation. We know that this distance is going to increase when the theta is increasing. So increasing theta will increase the d, and increasing the d will increase the torque. This is the reason. Stated direction is clear. It is clockwise, resistive against the more deviation. Determine the maximum angle theta max through which the meter stick rotates before it reverses the direction of motion. Here it has just kinetic energy, and here it has just potential energy, because we suppose that here the meter stick stops. Based on the conservation of energy, this kinetic energy must be equal to that potential energy. So the approach is that we put them equal and find the answer, maximum theta, because theta is related to potential energy. I can show you how. But you remember in potential energy we had mgh, and we had a very tacit, let's say, convention always in physics. The bottom point of a system that cannot go below that is taken as the zero and the ground state for potential energy. Okay, here is the ground state for that. It cannot go any more down. Okay, but what do we mean by h anyway? This in deviation it has a little bit higher altitude, but what do we mean by altitude? Altitude of which point? You remember in the center of mass I explained what do we mean by that. Actually, the center of mass is the point that we can consider all the mass of the object is concentrated there. So we should consider the center of mass. As this is a meter stick, let's say the distribution of mass is homogeneous, so center of mass is at the center of the rod. So center of mass will displace for this much, and this is exactly the h. So let's say the potential energy here is 0 as the ground state, and here we have the potential energy of mgh. Okay, so we should focus on center of mass. Okay, the meter stick has had a length of 1 meter, so half length is 0.5 meter. Okay, to find the h, it's very easy. Look, in this triangle, the hypotenuse is 0.5. Here I have theta, and then here I have 0.5 hypotenuse times cosine of theta. So this is 0.5 cosine of theta. H is supposed to be exactly 0.5 minus 0.5 cosine of theta. You see, H is related to theta. Okay, let's continue. Conservation of energy. Here it's just kinetic energy, here it's just potential energy. So we put them equal. Then I plug in the values. A half of I omega squared, the kinetic energy, we found it already, and it's mgh. Okay? And we will continue. We plug in the values, and then g is 9.8 here, and then h comes to be 0.2 meter. This is the h. Now we should relate the h to theta, because still we have one more step to find maximum theta. As this is the maximum h, so it's related to the maximum theta. How? Anyway, look at this. H is 0.2. This is totally 0.5, so this is 0.3. I subtract them, okay? So 0.5 cosine of theta is 0.3. Then cosine of theta is 3 over 5, or 0.6. And then theta is cosine inverse of 0.6, 53 degrees. It's the maximum deviation, maximum angle of deviation when it comes to rest. Thank you for your attention. Thank you for being with me. Take care. See you soon.